Hi everyone, today we are going to go over nuclear chemistry, and hopefully by the end of this video you will be able to understand what nuclear chemistry is and what some of the benefits and maybe even downfalls of the nuclear processes. So nuclear chemistry is the study of the structure of the atomic nuclei. So when we're looking at the nucleus, we're looking at protons and neutrons, okay? We're not really paying attention to the electrons in this case and the changes that they undergo. So the main ideas that I would like for you to kind of start thinking about in this process is nuclear power a good choice, and what is nuclear energy? Isotopes. So we're going to do a very quick review of isotopes. Isotopes are going to be your atoms of the same element that have a different mass number. So they have a different number of neutrons. You'll remember from previous lessons that mass number is going to be your top number on your isotope notation, and then your bottom number is going to be your atomic number. So your A would be protons plus neutrons, and your Z is your atomic number. An isotope is anything that has the same Z but a different A, and the symbol is going to be whatever element we're dealing with. So isotopes of atoms with unstable nuclei are called radioisotopes. So if we're looking at radioactive isotopes, stable isotopes are atoms that do not release protons or neutrons from the nucleus, and they're not radioactive. So they're stable, they're going to stand there. And if you remember from the build an atom activity, you saw stable isotopes versus unstable isotopes. Now an unstable isotope is a radioactive isotope. And for a radioactive isotope, you're going to have an atom that's going to spontaneously release protons and neutrons from its nucleus. So how do we know if it's going to be stable or unstable? Well, we look at this band of stability. So the band of stability is going to tell us if things are stable or not stable. And if you look at this band, so it's kind of this clouded region right here, okay? And if an isotope lands on the edge of that band of stability, then that's going to be a radioactive isotope or a radioisotope. Now notice if you did a 1-to-1 ratio right here, our 1-to-1 ratio is going to go along the line, and then it's going to go just underneath that band of stability. Now, as your isotopes get heavier, you'll realize that you no longer have a 1-to-1 ratio. Now, for larger atoms, you're going to have a 1-to-1.5 ratio. So if you look at your periodic table, you'll notice that you have way more neutrons for a stable isotope than you do protons. And that ratio you'll be able to find is like a 2-to-3 or 1-to-1.5. So again, smaller isotopes are going to have a 1-to-1 ratio of neutrons to protons. And you'll notice that that ratio kind of stays right there at up until about the atomic number, about 20, 25, okay? And then all of a sudden you start to kind of move away from that, okay? Larger atoms have a 1-to-1.5 ratio. So let's talk about chemical reactions versus nuclear reactions. Chemical reactions are not going to involve as much energy. Chemical reactions, we have mass conserved, and so that means that the mass doesn't change, and you have a small amount of energy, but no changes in the nuclei. So you're not changing the nucleus, you're not changing the number of protons, neutrons, and electrons. Whereas nuclear reactions, you have small changes in mass. So if you think about it, E equals mc squared, this is where it comes from. That's called binding energy. So the energy that is lost in that process is going to be equal to, or released in that process is going to be equal to the mass lost times the speed of light squared. So in nuclear reactions, we're actually changing the protons and the neutrons, and there's a large amount of energy. So nuclear reactions, one of the main ideas is nuclear reactions require a whole lot more energy than a chemical reaction does. So the mass defect. That's what we were just talking about. We were just talking about E equals mc squared. So some of the mass that's going to be converted into energy is going to be calculated through this E equals mc squared. So you figure out how much energy is needed to be converted, and then you divide by the speed of light squared, and that's going to show you what the mass change is going to be. Or you could look at the other way and figure out how much the mass change is going to be times the speed of light squared, and that's going to tell you how much energy is going to be released in the reaction. Okay, so radiation. We have three major types of radiation. We have alpha particles, okay, so alpha radiation. We have gamma particles, and we have beta particles, or gamma rays and beta particles. So notice beta particles have a -1 charge. Alpha particles have a +2 charge, and gamma rays have no charge and no mass, but they're really high energy. Positively charged alpha particles are going to end up being deflected by, so if you shoot this radioactive source to your charged plate, your electric field, your alpha particles are going to be deflected from the positive plate. And the reason for that is because positive is going to repel positive. Your negatives are going to be reflected from the negative plate. Again, like charges are going to repel. Now, something that's really important for you to recognize is alpha particles can do a lot of damage because they're a lot bigger, but alpha particles can only get through so much. So you could actually stop alpha particles with paper, metal, foil, or thin clothing. So the alpha particles aren't going to get through thin clothing, but if they did get through something, then you're going to end up having some issues. Beta radiation is the next in size, so it's going to be in the middle size. Beta radiation can be stopped by metal sheets, dense wood, or heavy clothing. And then gamma radiation. So gamma radiation has no mass and no charge, but it's the hardest to stop. And so you really need thick walls of lead or concrete to stop this, okay? And so again, when we're looking at size, the biggest is your alpha particle, but it's the easiest to stop, but can also do the most damage. Beta is in the middle, and then your gamma rays can get through the most because it's the smallest. So if we look at alpha particles versus beta particles and gamma particles, you'll notice that alpha particles have a charge of +2 and a mass number of 4. And we're just talking about nuclei. We're just talking about particles coming from the nucleus of an atom. Beta particles have a -1 charge, and the mass, there's not going to end up being a mass change involved in that, okay? So what you would see is you would see a change in the atomic number, but you wouldn't see a change in the mass. And then gamma particles have no mass and no charge, but they're going to, remember, they're the smallest particle, so they can penetrate most things. So again, this is just another graphic of an alpha particle versus a beta particle versus gamma radiation, okay? And so think about it, like the last time you went and got an x-ray for something, for maybe you broke bone or you got an x-ray for your mouth, what you're doing, you're putting on that lead vest or those lead plates, and you want to make sure that you're blocking the radiation. So alpha decay. Alpha decay, we end up having what's called our parent nucleus, and our parent nucleus produces our daughter nucleus. So what's produced is called the daughter nucleus. Now notice in alpha decay, we have our mass number, and our mass number changes by 4. So you drop your mass by 4, and also your atomic number drops by 2. So you drop by 2 for your atomic number, so -2 protons, and then if you -2 neutrons, that's equal to a mass change in 4. Now notice, it's really important for you to see, if you look at your yield sign for a chemical reaction, so what's produced in the end. So if you have 148 in the beginning, 148 is equivalent to 4 plus 144. So if I can add these two numbers and get what I have on the other side, I'm in good standing. If I have my 2 down here, 2 plus 62, that's going to end up giving me my 64. So for an alpha decay, the nucleus is splitting into 2 smaller elements, one in which is helium. And 2 protons are going to be lost, 2 neutrons are going to be lost, and so this results in a loss of 4 in your mass number. Beta decay. Beta decay is really and hopefully you saw this in your Gizmo lab, which I really like, but beta decay is really the loss of a neutron, and that neutron splits into an electron type particle and a proton. And so what ends up happening with beta decay is we end up releasing, this is a beta particle, and the beta particle has a -1 in the charge and then 0 mass change. And so you'll notice 20 is equivalent to 21 minus 1. So if we do -1 plus 21, we end up getting 20, which is the same as the parent nucleus or nuclei there. So we have, again, the parent nuclei and the daughter nuclei. So gamma rays are high energy particles, and they're released in these nuclear reactions. They have no change in mass and no change in atomic number. They can't be seen, but they can do a lot of damage. Okay, alpha particles, beta and gamma particles can be harmful to living organisms. And so if you think about it, like, we're going to end up getting into cells, and you can destroy cells with this radiation, right? So just some more review on alpha particles. If you look at this, you have your parent nuclei, and your parent nuclei ends up releasing this alpha particle. So the alpha particle splits, and you end up having your daughter nuclei plus your alpha particle. So you have a loss of the nucleus of a helium atom. So again, right here, you see 238 yields 234 plus 4, and you have the daughter nuclides. The parent nuclide, or nuclei is what I call it, and then your daughters. So you have 90 plus 2 equals 92. For beta, you end up having a loss of this beta particle. And so if I wanted to draw beta, that's going to be my symbol for beta. And if you're wondering for alpha, alpha is kind of like your little backwards, your fish, okay? But if you look at that, what you'll see I went from carbon 14 to nitrogen 14 with the release of my beta particle. But I changed my atom. I changed the atom that I was. I went from carbon to nitrogen, but I did not change my mass number, okay? So for your gamma particle emission, gamma rays are going to be high energy, short wavelength electromagnetic radiation. So remember, we just got finished talking about electromagnetic radiation. Something I want you to see is that everything that we're doing in chemistry all kinds of builds on itself, and kind of like everything meshes with each other, okay? And then hopefully you'll start to see where the stuff you learned in biology meshes with the stuff that you're learning in chemistry. As you can see from the symbol, both the subscripts and the superscript are 0. Therefore, your gamma ray does not change the atomic number or the mass number. Gamma rays almost always accompany alpha and beta radiation, as they account for most of the energy loss. So you have this high amount of energy, but no mass, no charge. So what if we wanted to figure out how to balance nuclear reactions? And you're going to be doing this in some of your activities, so I think it's really important for you to look at this. For balancing nuclear reactions, the sum of the mass number on each side must be equal. The sum of the atomic numbers, or the nuclear charge, on each side needs to be equal. So in this example, we have 92, and 92 is equal to plus 90. And then right here, I have 82. 82 is -1 plus 83. So what about here? If we look at this, we have our parent nuclide, and our parent nuclide, we have 85. So 85 going to bismuth, and if we look up bismuth, that's 83. So what's that going to produce? Well, 83 plus 2, and then 213 plus 4 is going to be 217. So really, we end up getting this helium nucleus, okay? And then if we look at our next one, thorium, 231, going to beta emission. So if we look at thorium, thorium is 90. So -1 plus what equals 90? That would be 91. And then 231 plus 0 is going to be 231. So we have Pa 91. So how do we know that's Pa? Okay. Well, we know that because we know that the 91 designates the element. So then we look on our periodic table to see what the symbol is. This next one, we have thallium 208 and beta decay. So we have thallium, and that was at 81. And so we have 82 minus 1 gives me 81. And then 208, that ends up giving me lead. Okay, so our nuclear reactions, we have two different types of nuclear reactions. We have fission reactions and we have fusion reactions. Fission is when nuclei split. Fusion is when they join together. Both of these reactions require a whole lot amount of energy, okay? And you've seen this in some of your activities. Nuclear fission is the splitting of one heavy nucleus into two or smaller nuclei, as well as some subatomic particles. A heavy nucleus is usually unstable due to many positive protons pushing apart. When fission occurs, energy is going to be produced and more neutrons are going to be given off. The big thing, though, is number one, I want you to understand that you have a lot of energy in this process. And number two, you have something big is breaking into two smaller things. Fission, it's fizzling apart. So this is an example of a nuclear fission. We have a neutron goes into your nuclei, attacks your nuclei. We have a release of gamma particle, and then we have that unstable isotope, gamma particle, beta particle. We have a new product, okay? Neutrons are used to make the nuclei unstable because it's much easier to crash a neutral neutron than it is to crash a proton. Why? Because you've got this positive charge here. You don't want to pull in a positive charge because that's just going to repel. So neutron's the easiest thing to attack. And so in your fission, you end up having a chain reaction, basically. So fission, and then you have a break, and then a break, and then a break. So this is called a chain reaction in fission. Nuclear fusion, you're fusing things together. You're pushing things together. So when you're joining two nuclei, that's going to be fusion. You're making it heavier. Fission, breaking it up. Fusion, making it heavier. Okay? This is going to happen in places like the core of the sun. It has to happen in stars, and it's because it requires so much energy. So in the sun, you can have two hydrogen nuclei can join together to create helium, okay? Bet you didn't know that that's how helium was formed, but that is how helium is formed. When the helium atom is formed, huge amounts of energy are going to be released. But here's the deal. So some people might say, well, why don't we use this for a safe, like for another alternative fuel? But the problem with fusion is scientists really have not found a safe way to manage and harness the energy of nuclear fusion. Now, scientists have been able to do it for like a second, but this is definitely an area where scientists are working on to see how can we harness the energy from a fusion reaction. So what are some of the applications that we can use for nuclear chemistry? You can use it in medicine with chemotherapy, power pacemakers, diagnostic tracers, agriculture. You can irradiate food as a pesticide. You can also use it for energy, okay? So right here, if you have an X-ray going through luggage, that would be an example of using nuclear radiation. You're irradiating food. So food can be irradiated from gamma rays from, you have cobalt-60 or cesium-137. Irradiated milk actually has a shelf life of 3 months without refrigeration, which is crazy. And a cancer patient in this case is receiving radiation therapy. So these are all of the different areas where you could use radiation. But then there are also some bad effects. We have the world's first atomic explosion. This was actually in New Mexico, okay? Because I don't know if you know that. Hopefully you learned that in your history class, but that's where the first atomic bomb explosion was, is a test site. So that would be one case of a bad effect of nuclear reactions. This is an after the explosion of Hiroshima on August 6th of 1945. So here's another picture of radiation and nuclear reactions and how that's affected. Power plants, okay? Think about San Onofre. San Onofre is a huge, like, that's a landmark, right? And so there you have your power plant. Now, obviously, people know that that's been shut down, but it's kind of interesting to think about the possibilities of nuclear power, okay? What about a nuclear power plant like this in Chernobyl? Okay, Chernobyl, with the Chernobyl accident, I mean, that whole area was affected, and the babies who were born were affected. So you have to think about the public health issues as well. So one of the things that we need to think about, though, one of the challenges with nuclear power is the disposal of waste products. So you have this hazardous waste, and so what are you going to do with that hazardous waste? Are you going to bury it underground? Are you going to put it in the sea? I mean, what are you going to end up doing with the hazardous waste? Because you have these fuel rods. And so are you going to reuse the fuel rods? But what about the waste that you can't reuse? What are you going to end up doing with them so that they don't, that waste doesn't affect living organisms? So there are two last things that I want to talk to you about just to make sure that you have gathered that from this review of nuclear chemistry. And I want to just real quickly review. In nature, we have four fundamental forces, and you've seen this in the videos that you've kind of looked at. We have your electromagnetic or your electrostatic force. Okay, so think about it like this. Think about it like your Coulombic force. Then you've got your gravitational force. Okay, gravitational force is like what keeps your butt on your seat, but also not just that. The gravitational force is the force of attraction between two massive particles or two massive bodies, no matter where they're located. And then you have your strong nuclear force and your weak nuclear force. So your four fundamental forces are electromagnetic force, gravitational force, strong nuclear, and weak nuclear force. So something to think about when you're talking about these forces is protons and neutrons are going to be held together with your strong nuclear forces, okay? Now, if you think about it, protons are going to repel each other, right? Because of electrostatic charges. But the repulsion is not strong enough to overcome that strong nuclear force. A lot of energy is actually needed to separate the nucleus, and this is because the force that holds the nucleus together, your nuclear forces, are going to be much stronger than the repulsive forces between the protons. Okay, so your strong nuclear force is going to be super strong. Now, one other topic that I wanted to throw in here is about half-life. And the reason I wanted to talk about half-life today is because later on throughout the week, you're going to be doing some things with half-life. So half-life is the amount of time that it takes for the nucleus of an atom to decay by half, okay? So radioactive decay is when that nucleus is going to spontaneously decay. And radioisotopes have what's called a half-life. And again, that is the time that it takes for it to cut in one half. This is the same type of decay or the idea that's used in carbon dating. So if we want to see how old something is, we can check the carbon isotopes and check to see how old that item is, okay? So the amount of remaining is going to be equal to your initial amount times 1/2 to the nth power. The nth power is how many half-lives have taken place, okay? But we really don't have to look at it with that full equation. Really, we can just look at it logically. So if we look at this question right here, it says iron 59 has a half-life of 44.5 days. So every 44.5 days, it's going to cut in half. So how much of a 2 milligram sample will remain after 133.5 days? So 133.5 days is the amount of time that has taken place. So we have 44.5 plus 44.5, okay? And you have 44.5 plus 44.5, you have 89 days right there, okay? So if we have 89 days, that's 2 half-lives. And then plus another 44.5 days. And that's going to be 133.5 days. So we know that we have had 3 half-lives taken place. So we have cut that 2 milligram sample in half by 1, by 2, by 3. So 2.00 milligrams times 1/2 times 1/2 times 1/2. Okay, so you're going to go from 2 to 1, 1 to 0.5, 0.5 to 0.25. So we're going to have 0.25 milligrams is going to be left after 133.5 days. So again, you figure out how many half-lives have taken place, and then you cut the sample in half, however many times that is. So let's try another question. How long is the half-life of cobalt-60 if 6.25 milligrams of a 50 milligram sample remain after 21.08 years? So if we look at it this way, we go, okay, I have 50 milligrams. 50 milligrams, and when I cut it in half, I get 25. I cut it in half again, I get 12.5. Okay, and I cut it in half again, I get 6.25. So I'm ending with 6.25. How many half-lives have I taken? I've taken one half-life, I've taken another half-life, and I've taken another half-life. So 3 half-lives equals 21.08 years. If 3 half-lives equals 21.08 years, then how many is 1 half-life? So what I'm going to do is I'm going to go ahead and pull up my calculator, and I'm going to do 21, and I know it's going to be close to 7. 21.08 years divided by 3. So if you're asking yourself, how did you get that 3? Well, I needed to figure out how many times I cut it in half. So I want to go from what my initial sample was to what my final sample is. So 50 divided by half is 25. Divided by half is 12.5. Divided by half is 6.25. Okay, or divided in half, not by half. And so that gives me 3 half-lives. 3 half-lives is 21.808 years. So 1 half-life is equivalent to 7.03 years. And so I figured out how long a half-life is. Hopefully that was helpful for you guys. If you have questions on half-lives or nuclear reactions, please go ahead and reach out.